Today we are going to do one more important article, or we can say that the most important article of the application of Gauss theorem. Now we are going to derive an expression for the electric field intensity due to a very infinite size thin plate sheet. So let's start now. Let there is a positively charged sheet and sigma be its surface charge density. Now let us consider a Gaussian surface. Here we have considered the cylindrical Gaussian. For the mathematical purpose, it is quite convenient. So let R be the radius of this cylinder and small l is the length of cylinder. One point should be noted here. The field line due to this charged sheet will be parallel, straight and uniformly spaced. So that is the key point. We will have to remember this key point. There is a point A on the flat part of a cylinder and ds be the area vector at that point, and it is parallel to the direction of field. Let P be the point on the just opposite face and ds be the area vector at that point, and it is also along the direction of field. It means theta is 0 for both cases. Let us consider the point C on the curved part. Let ds vector makes an angle 90 degree with respect to the field direction, as the field is just away from the plate. So here the ds vector will be at 90. Gauss theorem, we can say that the total flux is equal to the q upon epsilon naught. That is the statement from the Gauss theorem. Now let us evaluate the total flux due to this entire geometry. So as you know that we have already chosen the 3 point A, B and C. So the net flux will be given as the sum of all these, like this: E dot ds for the face A and the E dot ds for the face B. Now these two are the flat part, and now the one of the most important is third one is E dot ds for point C. Are you getting that? We have considered 3 phase and we have already stated the angle between the E vector and area vector for all the 3 cases. So we can write like this. For the point A it will be EDS cos 0, and for the point B it will be very similar to the first one. Now the third one is very important. It will be EDS cos 90, and as you know that cos 90 is 0, so you can say that this part, the flux due to the curved part, is 0, and only the contribution to evaluate the total flux is obtained from the flat part, that is from the A and B. Look at here. So the total flux due to this geometry will be twice of E, and now you know that the flat area is circular in shape, so its area will be pi r square, and our expression becomes 2E into pi r square. So we can see that the flux will be like this: q upon epsilon naught is equal to sigma into pi r square upon epsilon naught, where sigma is the surface charge density. That is quite obvious. So therefore we can say that our expression becomes 2E into pi r square is equal to sigma pi r square upon epsilon naught. So now the pi r square, that should be cancelled out. So we can write like this: E is equal to sigma upon 2 electric field intensity due to an infinite plate. And since E is a vector quantity, so we will have to write like this: E is equal to sigma upon 2 epsilon naught I cap. It means the direction of field is just outward with respect to the charge plate. If we consider the negative plate, then the direction of field will be inward. It means at the place of I cap, it will be minus I cap. Now, one important thing, just note it here. The electric field intensity is independent from the size of the plate or the size of the Gaussian surface, which you have already constructed. That's why we have chosen the cylindrical surface for the simple purpose. And it neither depends upon the distance of the point of observation with respect to the plate. That is the very important thing. But regarding the large flow articles, as you know that due to a point charge, E depends on the R, but here the intensity of electric field is totally independent with respect to the distance. If you like this, then give the comment like this.
Movember. Joshua.
If you don't like this, then give the comment like this.
Dr. Watson. Aage.